It's a pleasure to introduce my friend Bill Freeman. Bill got his PhD with Perkins, if I'm remembering correctly, at MIT. And after stints at Merle, other places, he's now split, strangely enough, between university and Google. He's managing to run successful groups at both places. Bill is his research is perhaps best characterized by the intersection of machine learning, computer vision, and computer graphics. But this is kind of an understatement because Bill is one of those few people who I think is quite credibly a program chair for the leading conferences in all three areas, which is actually kind of amazing. Finally, Bill is just an amazingly nice guy, and we always wonder, how can someone who's got such great research stuff be such an incredibly nice, modest guy? I finally figured it out. I looked carefully on his CV, and he has a Cornell degree. So, the mystery is revealed.
Oh, thanks so much. Well, thanks for the invitation to be here. So, Ithaca, can you hear me? Is that yes? Okay, good. Thank you. Right. So, thank you for inviting me to Cornell Tech. And yes, Cornell is where my wife and I met, so it always has a special place in my heart. And so I have this split life. I have two jobs. I work at Google and I work at MIT. And ostensibly, it's 80-20 Google, MIT. So they're across the street from each other, and I go across the street, and I'm at MIT like 2 afternoons a week. In practice, it's 80-50. And I, do wrangle my MIT email on the evenings and weekends, and that's pretty much how it is. So I want to tell you about sight and sound, audition and vision. And it's a new area for me to have gone into. I want to kind of describe it in an idiosyncratic way, like not a survey of the field, but a survey of how my lab got into this. So I want to kind of tell you our story for getting into audition and combining it with vision. Oh yes, and then okay, I started at Google on a sabbatical leave, and the lawyers, it took them 6 months to come out with the rules for what I do where. And after 6 months, they finally come up with the first thing that you would ever think of, really, which is that what I do at MIT stays at MIT, and what I do at Google stays at Google. Now, in contrast with that, this talk describes work at both MIT and Google on kind of the same topic. So anyway, that's how it is. That's the way it goes. But so I want to first tell you about how we got into Vision plus Audition from the MIT lab, and then at the end, sort of the second half of the talk, tell you about a really fun Vision and Audition project from the Google lab. And I'll tell you when that transition happens. So I got into studying vibration and audition through motion magnification. So motion magnification is this fun algorithm we developed that makes a microscope for motion. On the left, you see the input image of a baby breathing, and on the right is the motion magnified version of it, with the small amplitude motions made larger. So it's the video that you would have seen if the motions in the left video were amplified by a factor of 40 or so. And it's really, and also this tells a little story about the field of computer vision. We started this back in the pre-revolution days, when we did things analytically and we thought about the functions and we designed things. So how we did that in the previous frame was really simple. We took an image and broke it up into what's called a steerable pyramid representation. So in Ithaca, if I point to a screen, can you see that? No? But you can. Oh, wow. Okay, great. So, so here's an image, and we break it up into this multi-resolution oriented filter representation. So these are some of the basis filters. And so at every position, orientation, and scale, you have a pair of filters, a sine phase and a cosine phase filter. And you measure the phase response of these filters over time, which tells you about tiny position, tells you very accurately about the position of these things at this particular position, orientation, and scale. So then you're almost done. Now all you have to do is say, well, pick out the temporal frequency band you want to amplify, and pick out how much you want to magnify it by, and take those phase changes and amplify them by that amount. And then you go back from this steerable pyramid representation back down to the image domain and just do that frame by frame. It's really simple. So there's the architecture for it, and you can. It's a wonderful tool that lets you look at small oscillations in the world, and that's how we're going to get into sound. But before we get into sound, I just want to show you some of the fun things you can do with this. Here's a big oscillation in the world. This is a bridge in New Hampshire. Not shown off to the right, there's a drawbridge that comes down and gives it like an impulse kick, but you can't see it. So here's the input video that we took from across the water, playing at ordinary speed and no amplification of the motion. Now let's take that same video and amplify the motions of a particular vibrational mode of bridge. And this is the motion magnified video of what we just saw. And you can see these, this vibrational mode that you could probably feel if you're on the bridge, but you can't see it. And so again, it's a microscope for motion. This one I really love. So when someone stands on one foot and balances, like a ballet dancer who can do it seemingly effortlessly, you know that there's got to be all these control forces going on to keep the person from falling over. And now we can visualize those. So here are the controls that the professional ballet dancer has to do to keep from falling down, standing on one toe. But now we're going to get to sound. We're going to video someone's throat as they articulate a noise. So here's Mickey, who did a lot of this work. We're going to listen to him sing, if you will. Darn it. So here we have our first baby fail. All right. Okay, we have a workaround. Sorry. So Jessica, can you hear this? Can you hear that? Can you hear that? Okay, fine. So we'll do it that way. Fine. So there's him making sound. Let's motion magnify the high-speed video of his throat as he made that singing sound. So there it is. And so we've we narrowband filtered the audio to only amplify those temporal frequencies, and you can see the motions in his throat as he made that sound. Okay. So we made a live demo of it. Let me stop for a second. Now, you've heard this thing about, well, if you take a wine glass and you ping it, and usually I bring one, but I forgot to bring one. It goes ding, ding, and so it's vibrating, but you've never seen it oscillate. Why not? Well, there are two reasons. One, what's one reason? Too small amplitude vibration to see, okay. Two, what's the second reason? It's too fast, excellent. So we're going to address both those with this demo. We have a special camera that only grabs 1 millisecond every frame. And so we're going to alias down the fast motion down to about 2 or 3 hertz. So they'll be slow enough to see. And then, you guessed it, we're going to use motion magnification to amplify the size of that motion so we can actually see it. So on this, I'll play it again. On the left side is the alias down but not motion magnified video. And on the right side is the motion magnified video. And we're going to turn on the speaker, which makes this annoying sound. And you can watch the wine glass move in sympathetic vibration in this real-time demo that I'm showing you a video of. So there's the sound. And now you can see the wine glass move in sympathetic vibration. And so now you've seen a wine glass oscillate. So that's the motion microscope. And by the way, this is tangential to this talk, but I'm looking for the killer app for the motion microscope. So far, the killer app is amplify baby's breathing so that nervous parents can check that their baby's breathing, okay? But there's got to be something better. And I think it's going to be medical applications. The stereotypic picture of a doctor is someone who has a stethoscope around his or her neck. What is a stethoscope? A stethoscope is a motion magnification device that takes small audio vibration sounds and makes them audible. And so if that's so diagnostically useful, surely it will also be diagnostically useful to amplify visual signals that are very small amplitude vibrations and make them visible to the physician as well. So I'm hopeful that there might be applications there. Okay, but now we're moving on to sound plus vision. So we could see small oscillations and see them moving as something made a sound. I wonder if we can see it moving as something has a sound made toward it. So we've got this idea, and again, this is all driven by the students, but to use a bag of potato chips as a microphone. And so we're going to play some sound at the bag of potato chips and watch it oscillate, and then pick up what the sound was. Okay, so what are we seeing there? These are different narrow frequency band tunings, motion magnified, of the bag of potato chips as this Mary Had a Little Lamb is being spoken to the bag of potato chips. And you can see it move in response. And the spectrograms of the raw audio signal and of the recovered audio signal are shown in the left and right respectively. So it's kind of a lousy microphone. It doesn't have great high frequency response, but it works as a microphone. You can measure audio from watching from the video.
Hey, Bill.
Yeah.
There is something totally obvious. That's just the sort of problem that CNN is still trying to go, because you have to recover. You have what the spectrogram should be.
Okay. The comment was, use a CNN, you can do much better.
Shockingly enough. That probably.
Yeah. Okay. And then here's another one. This is a visual spectrogram. So we see these little videos, each one tuned to a narrow band temporal frequency, and you can watch it oscillate when this tune comes to the different point in the song. And I'll put the microphone close up here so you might be able to hear it. I don't know if you can hear that at all, Ithaca, but or New York. Okay, so that's how we got into it. But it raises a lot of questions. Namely, is there a synergy between vision and audio? And what do we learn from audio that's different from what we learn from vision? And again, this is an idiosyncratic tour, but there are, I'm sure, deeper insights than I'm going to show here, but these are kind of things we were thinking of. Let me play some sounds, and so I want to play some sounds of an event, and then show you a picture of an event, and see which one gives you better information about that event. What do you think's going on?
Water dripping.
And I sure hope you can hear that, Ithaca. But anyway, so any comments, any thoughts? What is this?
Is it like water dripping on, like slowly dripping onto like a metal or something?
So the comment was, is it water dripping on metal? Well, kind of. So here's the visual version of what we saw, and it's eggs cracking. And so, you get different stories with these. You get sort of much better. Some parts come across much better in the audio, some parts come across much better in the video. And you might ask, so vision, well, it's limited by occlusions, it's got limited line of sight, but it really tells the story in a very full way that sometimes audio doesn't. So you might want to ask, how do these two interact? Can you learn something from one that you can't tell from the other? If you hear both at the same time, hear and see at the same time, can you learn new things? So I was talking about this with a friend, and he said, oh yeah, it's well known, there's a kind of a folk story, that people can hear better when they get glasses. Has anyone experienced that, by the way? Okay, there's a yes. And my friend said that's kind of a thing, that people hear better when they put their glasses on. So you might imagine, could you improve the audio recording of a symphony if you have access to a video of it playing at the same time? And you can imagine if it was a really lousy audio and you had video that showed exactly when the violins were going, that it might tell you how to interpolate sounds across, there should be constant that are not constant in the audio, some things like that. You could imagine some help there. And then the converse is also interesting. Is there ever a case where you could improve visual quality by listening to the audio of what you were looking at? And it's a little bit harder to come up with a case where that might work. The only thing I could possibly think of was, maybe if you have some forest scene and you hear the exact rustling of the leaves, maybe you could synthesize things moving to explain the audio that you couldn't see visually. But then also there's things, how you can learn from one another. If you hear and see at the same time, that's really going to tell you a lot of information about what's going on in the world, more than either one alone. So that's really what I want to focus on, is how to exploit both at the same time to learn new things or filter things you couldn't otherwise. So what follows now are kind of two short talks, an MIT project talk and a Google project talk. So the first one is predicting visually indicated sounds, which we also say, what can you learn by hitting everything you see with a drumstick? Okay, so what can you learn? Let's try it. You can tell a lot about these materials when you hit them with a drumstick. And so it excites them, they start to oscillate, and based on their mechanical properties, it reflects a certain sound, which really tells you a lot about its mechanical properties. And we're not the only ones who explore the world this way. Here's a young scientist exploring with vision, audio, taste, all at the same time, and really learning about the world. And so, and also, I told you I had these two hats, the industrial and the academic researcher. My academic version of myself really wants to find problems where I'm not going to be beat by Google and Facebook and all those other people with big data sets. And I think that realm is going to be unsupervised learning. And so I can take as much video as anyone can and record audio at the same time, and I want to be able to exploit that to be able to learn from unlabeled interaction with the world rather than this very awkward method that currently works best of having everything labeled and learning from that. So that's another reason to explore this. So this project then is one little slice of the more general program of kind of unsupervised learning about the world from interaction with it. So rather than having a graduate student or someone label all the materials in every single video that you see, we're going to send a graduate student out into the world and have them hit everything with the drumstick and record video and audio at the same time, and use that as a proxy for labeling the materials of what you're seeing in the world. So that, Andrew Owens, who's now on the job market, by the way, he spent a not trivial amount of his graduate career asking people, can I go into your office and hit everything with a drumstick? And so he made this data set of 46,000 hits or scratches of all these different materials. And what do you think he called this data set?
Drumstick.
Drumstick, okay. He had, I think, an even better name, which was the greatest hits data set. So, and now, let me just play some of the greatest hits data set for you, okay? And 45,000 other ones as well beyond that. But first of all, note how much you really learn about things by seeing them both together. You really get a sense for what the materials are that are being struck or scratched. And so we want to so the input is that raw data, and the output is going to be learning some representation for the material properties of what you're looking at. That's the desired unsupervised learning project. And so what are some ideas? So suppose someone handed you this data set, video plus audio, all these things being struck. How might you use it to learn the look of the materials and their properties? What would you do with this data set if someone handed it to you? Okay, well, let me tell you what we did. We wanted to turn it into into a supervised task, into a prediction task. So we're going to say, let's try to predict what the audio would be from a silent version of the video. Now, if you could do that, then our story is that then you've learned something about the material properties of what you're looking at, because you wouldn't be able to generate the proper audio unless you knew, that this was wood or this was water or something about its material characteristics. So that's the machine learning task. And then, times being what they are, given the task and the data set, we're almost done, okay? So step one, collect the database, we've done that. Then the remaining steps are pretty straightforward, really. Select representation for the audio, a representation for the video, regress from the video to the audio, and evaluate the results, okay? So I'm going to kind of skip over those, but let's talk about them. What would be a good representation for the audio, do you think? Come on, you gotta start raising your hands here.
I heard someone say something.
Yes?
Someone said spectrogram back here.
Spectrogram, yes! Bing, bang, bing, bing. That's what we use. So you could imagine using just the waveform of the audio itself, but to be able to synthesize that correctly, you've got to get everything exactly in phase, and it seems like it'd be really hard. And much better would be a representation that kind of captures the essence of the perception, but in a more, less fragile way. And so that's the spectrogram. So you take the signal, take its Fourier transform, and break into these two axes of temporal frequency and time. And so you get representations like this. So here's time along the bottom axis, and audio frequency going this way. So load high. So a cushion makes a thud, and so it has a lot of low frequencies and not too many high frequencies, and it all happens at this one time when you strike the cushion with the drumstick. Okay, and then and different materials have different spectrograms, and really according to material. So if you could predict the spectrogram of what the thing would sound like when you strike it, then we assert you have some understanding of the material, and you can then go and regress from spectrogram to material to actually come up with a label if you want. Okay, video. What's a good representation of the video? Okay, these questions aren't going to answer themselves, but I guess I will have to answer them. Well, we just have to use neural networks for that, because there's been so much progress, and they are such wonderful features. So we're going to take the input video, and yeah. So we're capturing time in two different ways. One, this is really ugly kludge. We're taking 3 consecutive frames of the luminance, and we're going to put them in the red, green, and blue, respectively, channels of an image, and then take this and run it through ImageNet, and that's our representation for the video, frame by frame. So we have time represented here in this little offset pseudo color code, and then in addition we're going to then we take it and run it through a sort of AlexNet representation to give us the features for the video, and then we have to regress from one to the other, and for that we'll use LSTMs and CNNs in the sort of conventional way. And there's not too much more to say about that. And then we evaluate the results. So we trained up the network to predict. And so what we have now is a machine where you put in a silent video of someone hitting things with a drumstick, and we're going to generate an audio from that. which we hope will sound plausible if we solve the problem of being able to estimate some representation for the material property of what's being struck. So let me show you the results. I mean, obviously there's more to it. I guess the main thing that's more to it is what we really come out with is a spectrogram. Then you need to go from a spectrogram prediction to the actual audio waveform. There are a number of different ways to do it. We used an example-based approach where we went to our data set, found the audio clip that best matched this spectrogram, and played that. Okay, so I can hear that well up here. Can you in the back hear that sound? Okay, good, thanks. So it sounds, you know, seems to have a rock-like sound to it. Let's do another one. So again, it seems to respond differently when it hits rock and bush. This last one is how we evaluated it. So we played it, our synthesized audio and the true audio, and asked a user to say which one is the real one. You want to try that again? Let's see how it goes. How many think the left one is real? How many think the right one is real? Okay, and the answer is the right one is real. And you know, so we did this many times. How many think the left one's real? How many think the right one's real? You got that one better. Sorry, and that one is, yeah. There, so the left one was real. The right was predicted. So how well did we do over many different trials, many different observers? We fooled them 40% of the time. So you might argue that perfect performance would be 50%. It's actually hard to know what perfect performance is. There are some times when you strike it and there's leaves on the ground and you hit a rock underneath the leaf. And so it doesn't sound, so the right audio doesn't sound quite right because it's not what's visually shown in some sense. So it's hard to know what really the best, what perfect performance would be, but we think it's pretty good performance. And just for comparisons, if we did it, let's see, I think this is just taking a static image and matching it. We got 33%. And if we picked a random audio from our database and played that with whatever the video was, it was chosen 20% of the time. So that gives you a sense for chance performance. And then you can go and take these predicted spectrograms and regress back to materials and come up with a confusion matrix to show that this does, in some sense, learn about material properties in the world, modulo how much their sounds are confused with each other by themselves. So that's that piece. I sort of want to move ahead a little faster, but go ahead.
So did you look at if you change the drumstick, like to a metallic drumstick or a thicker drumstick, and if you could generalize across?
Right. So the question was, you know, the drumstick is making some sounds here too. What if you change it to a different drumstick? We didn't explore that area. We kept this drumstick constant, so all the sounds had the resonance of this thing folded in. Actually, let me just jump ahead to part B of this because it's really fun. This is kind of a summary of what we did on the MIT side. Now let's go to the Google side. And also, by the way, all these institutions I'm involved in are looking for people. So if you're looking for a postdoc, give me a call. If you want to apply to graduate school at MIT, give us a call. And Google, too, if you're looking for a job, give us a call. If you're looking for summer internship, give us a call. Anyway, everyone's looking for people. But this is my Google team. And we do research on computer vision, graphics, and machine learning.
Where did Gerd start go to school?
Sorry?
Where did Gerd start go to school?
Oh, and I'm contractually obligated to point out the Cornell graduates in this picture. Here's one, here's one. I think that's it. What?
Gerd doesn't have the presidency.
Oh, I see. Oh, that's, Thank you. I'll fix that next time. Okay, so looking to listen. Here's the idea. You're at a cocktail party. All these people are talking, but we're pretty good at disentangling that. If we can look at someone and see them talking, it's much easier to hear them than if we can't. And let's try to let a machine do that as well. So here's the desired thing for this is to take video and audio, specify the face you want to listen to, and use the video to filter the audio to only play the sound of that person speaking. Okay, and when we started this project, we thought, well, okay, you can also do that with beamforming with microphones. So you could have like 5 microphones. You could also address the problem that way. Do we want to do both, one or the other? Let's just make it all simple and kind of modular so we can understand what's doing what in this case, and we'll just only restrict ourselves to the case of a single microphone plus video to try to filter it. And then you could always add in other microphones, or maybe you could use this to reduce the number of other microphones you need to save costs and so forth. So here is the task.
So the task is video. Any person who you see talking, their audio gets working out, and everything else gets suppressed.
That's me before using the algorithm. Here's using the results of our method.
So the task is in the video. Any person who you see talking, their audio gets working out. Everything else gets suppressed.
So that's the goal, and that's the output of the mechanism. Here's some more. So, we had fun with this. There are a lot of times on our video world that we consume where there are people talking at once. So here's another example.
He's not on a Danny Ainge level, but he's above a Colangelo level. In other words, he understands enough to...
You said it's all right to lose on purpose. You said it's all right to lose on purpose.
Yeah, of course.
And advertise as an offense.
Who doesn't know
It's perfectly okay.
So if you wanted to listen to that one speaker at a time, we can let you do it.
Don't explain it away now. Don't explain it away. You said it was all right to lose on purpose. You said it's all right to lose on purpose and advertise as an offense. It's perfectly okay.
So that's the output of our system.
He's not on a Danny Ainge
This is the other one.
but he's above a Colangelo level. In other words, he understands enough to... If I were a Sixers fan, of course, it's called thinking. Who doesn't know that?
Okay. And here's another one. Sorry, I just have to show these. So this is on the Conan O'Brien show. The premise was that they had inadvertently booked 2 comedians to speak on the same night. I don't really believe this, but that's what the premise was on the show. And so this was what they broadcast.
He might say, my stripes are solid. You know what I mean? I won't flush the night because of the noise. Like, it scares me.
So let's apply our method to this.
Think about a fan of flying. I hate being on planes. In general, there's too many noises. You know what I mean? I won't flush the toilet on an airplane because of the noise. Like, it scares me. You hit flush, then you turn around, nothing happens for 5 seconds, then out of nowhere, whoa! Oh my God! I just put a hole in the plane.
Okay, now you might ask, how much of this separation is leveraging off the video, and how much could you get if you just listened to the audio alone and ran it through a speech separation algorithm? So it turns out at Google we happen to have such a speech separation algorithm, which is probably the best in the world. It wasn't done by us. But I can play the results for that one. So this is audio only, trying to pull out the speaker on the right.
You hit flush, then you turn around for 5 seconds, then out of like, just the plane, it's perfect fine.
So the intended effect is, the furrowed eyebrows that I saw is the correct answer. It doesn't work as well to separate them. Let's see. Okay, I have about 5 minutes left. I'm just going to skip through the algorithm. I should say, I went to ICCV, the big computer vision conference in Italy, and I walked around the posters with my friend Pietro Perona, professor at Caltech. He said, Bill, when I look at posters now, I don't even bother to look at how it's done because I just assume the algorithm is going to work. I'm really just interested in what the data sets are, because that's what distinguishes one piece of work from another. So anyway, that's the state we are. So I'm going to emphasize what the data set is here that we made. Also, in the interest of time, I just want to skim over this really interesting fact that there were like 4 different groups independently came up with something that had a similar goal at the same time. And a few of us were friends, and we found out about each other's before we published them, and we all agreed to coordinate when we would release them on archive. So we actually did that, and so there were like 4 or 5 different papers addressing a similar goal that came out on archive at exactly the same time. What's different between them? This is ours, works really well, kind of a brute force approach, which I'll show you in a second. Kristen Grauman and Antonio Torralba had really nice ones which solved just a subset of the same problem. Alyosha Efros and my former student, now a postdoc with him, Andrew Owens, had this beautiful, elegant thing, which was really general. It didn't work nearly as well for this one particular task, but it covered many other tasks. So that's kind of the, and then Andrew Zisserman had one which worked really well also. So anyway, in terms of raw performance, I think these 2 are the best, but there's a nice spectrum of approaches that were applied. How do we do it? Again, the data set. So what do we use for a data set? Okay, what we need is noisy audio and then the true audio from the single speaker as our training set. How are we going to get that? Let's get it from lots of different individual clean audios, clean video of the person, clean audio, and we're going to synthesize our own noisy rooms by just adding together the audios to generate the difficult input of many people speaking all at once. So the place we got our clean audio and video from were TED Talks. And here's some examples.
Doesn't use radars like potential autonomous cars. Actually, in order to navigate, it only uses a vision system.
Okay, so there are lots of those on the web. Obviously, we omitted the parts of the TED Talks where the face had insufficient resolution or where the speaker was out of the frame. And these are some examples.
We work with people of all ages and all backgrounds.
Я верю, что меня ждет очень много возможностей.
The reason one would select a pen light over the other types of light.
Okay, that's the individual clean ones. And then there was a broad range of people and ages and genders covered. And then we synthesized our noisy cocktail parties. So here's an example.
Defense mechanism, we tend to go out of our way to avoid them.
And who within 3 years has halved that?
Defense mechanism, we tend to go out of our way to avoid them.
So we would take the one on the right as our input and train it to produce either the red bordered audio or the blue audio as the desired output during training. Let me just skip over this. We did several people, you could do as many people at a time as you wanted.
Enrolling a PhD in Europe.
All the data.
Two students enrolling a PhD in Europe.
And again, I guess I should stop soon. So here's the more meat of it. How do we want to represent the face? How do we want to represent the audio? There's a really powerful network called FaceNet, which takes an input face and converts it to an embedding that represents the identity of the speaker, removing the effects of lighting, size, pose, and all that. And that's almost what we want, but we don't want everything removed and remaining only with the identity. We're interested in removing the effects of pose, size, lighting, but we want to keep the effects of watching the face move and so forth. So what we did, we took this very powerful network and just went back a few layers from the very end. And we had explored this network before, and we knew that just a few layers before the very end of the final embedding, there was this residual stuff that would be gotten rid of later that was sensitive to the motion of the lips and the motion of the face, and yet it was insensitive to lighting and other conditions that we wanted to basically marginalize out. So that's what we used as the visual input. And for the audio input, again, we used short time Fourier transform, this spectrogram representation. And the desired outputs was not pure audio, but we we have trained the network to come up with a complex valued mask to multiply the audio spectrogram by, and the product of those two would be the desired output spectrum that we're going to output short time Fourier transform of the audio that we would then transform back and play as an audio. So in this modern era, here's the algorithm. You know, a set of weights and skip connections and convolution patterns and so forth. 19 million parameters, trained on 1.5 million mixed speech examples. The current version was 10 times real time. In other words, to process 1 second, it took 10 seconds. Now I can report informally that it works in real time. It works on device, on the phone itself. So now let me just show you results from here on out. And when should I stop, Robin?
Well, we got a bit of a late start, so why don't you go after?
Okay, let me do. Okay, I can probably stop at 1. So let me just show you more results.
Hi guys. So we've been trying to train this network to input to embedding as an alpha 3. Yeah, this is just an extra experiment of paper.
So if you were listening carefully, you noticed Hebrew in the background, but now it's filtered out.
Hi guys. So we've been trying to train this network to input to embedding as an alpha 3. Yeah, this is just an extra experiment of paper. And
I should mention, by the way, that these are the two primary movers on the work itself. The smaller figure, Inbar Mosseri, is kind of the engine behind the project, and Ariel in the foreground is the intern whose project it was. Okay, now you might say, oh, come on, it's probably just filtering based on frequency, you know, just based on the pitch or something. So let's give it a real hard problem where it has to look at the video to do it properly. Let's take the same speaker, same close, same time, same audio, and just shift it in time. So we have Sundar, the CEO of Google, talking over Sundar. And the only way you could possibly separate those out would be by looking at the video. So here's the input that we're going to challenge the network to separate.
For example, I use Google Calendar all the time. On Sundays, at a higher level, I get a big AI first work.
So here we go. We asked the algorithm to only play the audio corresponding to the left face.
At a higher level, in the AI first world, I believe computers should adapt to how people live their lives, rather than people having to adapt to computers.
And again, for comparison, suppose you tried to do that separation without access to the video. Here's what it would sound like.
At a higher level, in the AI first world, I believe computers should adapt to how people live their lives. Can be with more devoured and advanced.
So it doesn't really work, is the point of that. Let's just play this. So,
AI first world, I believe computers should adapt.
So how is it numerically? It's
having to adapt to computers.
So, you know, perceptually, we feel it's a big difference. In terms of numbers, it's about 1 dB difference improvement over audio only. Let's see what else. Oh yeah, and it's easier to separate females from females and males from females than males from males, according, at least in our experiments. So how might you use this? Well, we think there are a lot of ways you might use this. If you were Google, say, or Alexa or Amazon, or whatever, you have these devices that want to interact and respond to voice commands, but there's a lot of noise in the background. So Inbar concocted the scene, and she wants me to tell you that her children are really very well behaved, and she asked them to be noisy for this video. And I just want to say that on her behalf. Okay, so that's the input, and then the poor navigation device is trying to listen to all that and decide what to respond to. But if you filter it based on the video, you can give it a much cleaner signal, and it'll have a much better chance of responding to appropriately.
Okay, Google, please navigate to water. Okay, Google.
So this might have application in these Alexa type devices or Google Home, actually. Quickly add. And also you can improve captioning. So as an industrial research lab, we try to solve the problem of doing what we love and being valuable to the company at the same time. So we did what we loved. We did this project. We got into SIGGRAPH and had this sort of academic recognition that we wanted. And then was phase 2. Well, let's go push this to the appropriate product group at Google. And we tried a number of different product groups. We were successful. I can't really tell you which one we were successful yet, but here's some things that we were thinking of. You might imagine using it for YouTube captioning. So you could imagine that the captioning is not going to work well, automatic captioning, when there are 2 people talking at once. So I'm going to play this tape. They're both talking at once, and you can read the caption and see if you think it gets it right or not.
What do you want them to do? Have you read the testimony? I talked to the Department of Justice at length about this. Have you read the testimony that was given to the U.S. Commission on Civil Rights? It doesn't matter. They got an injunction against him. No, but they got an injunction against him. You clearly don't know what you're talking about.
Okay, so even though we can parse it pretty well, the captioning just can't come up with a single caption stream that properly explains it. But if you use this looking to listen, you can focus just on one person and come up with a pretty accurate caption from just that one person. Let me play that for you now. I believe we're going to come up with a caption for the person on the right.
To do? Have you read the testimony?
Oh, sorry.
What do you want them to do? I don't need to. I talked to the Department of Justice at length about this. They got an injunction against the guy. No, Megan, it doesn't matter. They got an injunction against him. No, but they got an injunction against him.
So there's one possible application. Just quickly, again, in this era, we don't know why it works or what it does, but we can try to figure it out, becoming biologists instead of engineers, and we perform these experiments where we ablate different parts of this input signal and see how well it performs. So let's make a little space-time box that we cover up part of the face, and we can make a map of what part of the face is most destructive to the performance of the audio filtering. And you can see there's the map. And here it is for several other people. What we found interesting, you can imagine that the lips are going to be really important, but we found interesting that other parts of the face were also important for this system to perform well. And again, as biologists, we have to explore further exactly why, but that was one of the results of our experiments. I guess one other application that would be in the future would be for a hearing aid. People who wear hearing aids tell me that it's really hard to listen in a really noisy room. And you can imagine having some glasses that look at where your eyes are looking and then have it automatically filter the audio to only play the audio of the person who you're looking at. And that might be useful. And let me just close then with this last clip, again from Sundar. This was him describing this work at Google I/O, which is their big annual event in the spring.
We have machine learning technology called Looking to Listen. It not only looks for audio cues, but combines it with visual cues to clearly disambiguate the 2 voices. Let's see how that can work maybe in YouTube.
Not on a Danny Ainge level, but he's above intellectual level. In other words, he understands enough to...
You said it was all right to lose on purpose. You said it's all right to lose on purpose and advertise that to the fans. It's perfectly okay. You said it's okay. We have nothing else to talk about.
We have a lot to talk about. But you can see how we can put technology to work to make an important day-to-day use case profoundly better.
So that's the second part, the Google part, and taken together, that's my story of my lab's interactions with audio and video, and how you can exploit synergies. And there's a lot to do there. It's an exciting area, and I invite you to participate. Thanks.
For surviving all the EV issues, as it were. We have time for questions.
Go ahead.
Have you gotten any? I really like your potential application. But have you gotten any pushback from like privacy-oriented people about having, the idea of like, I assume with like the hearing aids you need a camera, or with people who are already worried about things like Google Home listening to them or whatever. You're going to put a camera on it so that it can see them.
The question was,
have you gotten any pushback from these sorts of applications?
The question was, have we gotten pushback from people concerned that Google is looking at what you're saying? So, interestingly, the only pushback I've gotten was from a Google employee who happened to be in the background behind me when I said that thing in the cafeteria. And anyway, he was concerned that I was photographing video inside a confidential Google cafeteria and posting it on the web, even though you can't hear it. He said, well, but now you've got this technology that lets you hear it, and so yes, he had that concern. The short-term product applications we're talking about, I'm pretty sure don't really fit into those privacy issues. It's in terms of kind of things that are already, where you're already in control of the recording yourself, and so I don't think those privacy issues would be an issue, but I could see that down the line they would, yes.
Thank you, it's really super fascinating. This might be a silly question, but would it be possible to go the other way and like use the CNN on the audio data to synthesize images?
Yes, the question is, would it be possible to go the other way? Have input be audio and produce an image of the speaker. And yes, and we thought of that too, and we submitted a paper to CPR doing exactly that. Now, boy, you think there are going to be privacy concerns.
Yesterday in The Intercept, there was an article about how prisons in the US are recording voice prints of all prisoners, etc. So there's kind of like,
right.
There's potential down the line questions about those kinds of techniques.
Right, and for the people who couldn't hear, that comment was just concerned about audio recordings of prisoners or other people being used in bad ways. And so we agree, and we're trying to be really sensitive to those concerns as we write up the scientific results of that paper. Yes. Yes.
So for your kind of like visual microphone work, what kind of camera are you using? Is it something exotic or something that's like very easy to buy?
The question was for the visual microphone work, that was way at the beginning of the talk, what kind of camera do we use? So, so for that work, we actually wanted to record the vibrations themselves with the video camera. So we had to have a high-speed camera that could capture that. Although, again, these students are very creative. They realized, one student thought of this, that they could use an ordinary, cheap video frame rate camera that had a, what's the word? Rolling shutter, thank you. If you use a rolling shutter, then you kind of, as a side effect, grab some very high frequencies from ordinary frame rate video, and we could do it from there, although it sounded terrible, but yes. Yes?
Is it possible to predict the ambient sound for landscape photography? Because,
the question was, is it possible to have input be a landscape photograph, the output to be predict the ambient sound? We're really interested, all these questions are kind of raising issues that we kind of are interested in ourselves. We are exploring that as an academic direction. I think that's a really fun problem, and we think you can do something with that, yes.
Outside of facial occlusion, were there any like physical distance limitations in terms of like the audio?
And the comment was, apart from the facial occlusion as one restriction on this algorithm, were there other restrictions like size of the speaker and so forth? We didn't push that too much. As I mentioned, we restricted the training set to only include faces that were large enough to resolve well. We haven't really studied how performance degrades as the face gets smaller and smaller, but surely it will.
In your architecture, I know we don't want to talk too much about the architectures, but I noticed you were using dilated convolution as opposed to pooling to get sort of, multi-scale features. Is there any sort of hand-wavy principled reason? I know it's kind of, dilated convolutions are kind of, I think people are, giving more attention now, but was there a reason for this particular application that was useful?
Well, I'm sad to report that decision wasn't made by me. It was made by the people who were in the trenches doing the work, and so I really don't know the reason for that trade-off.
So for the research, like academic side, are you guys only research for Google, or are you open source for like working with outside company like other applications or stuff?
let's see, so there's two research groups that we talked about. One was the one at MIT, one is one at Google. The one at MIT is for you to do whatever. The one at Google, we can have some academic collaborations. It's a little bit harder to have industrial collaborations, with other companies. But sometimes if there's an academic involved, we can have like a triangle. But anyway, it's more company-to-company collaborations are harder. All right, well, thanks a lot. This was fun.